afternoon, everyone, and welcome to RIEGL's monthly webinar series. Today's webinar is titled Qualitative Analysis of Beam Parameters on the Performance of a Topo-Bathymetric LiDAR Sensor. Now, this analysis was made possible by Dr. Martin Fenningbauer, Peter Rieger, Roland Schwartz, and Dr. Andreas Ulrich. And I'll be presenting this information on their behalf. My name's Michael Sitar. I'm Managing Director at RIEGL Canada and the Airborne Division Manager for RIEGL USA. As far as an agenda is concerned, we'll start off looking at some of the RIEGL's Topo-Bathy sensors and some installation examples. We'll talk briefly about the variables impacting water penetration, and then showing some operational examples of the success of those different different variables. And then, of course, the focus of this presentation is on the beam parameter effects. We'll be reviewing water surface and bottom surface detection results and vegetation penetration success. And then finally, we'll complete this with some best practices and conclusions. For your information, there are in fact some handouts that you can download on the various sensors that RIEGL offers. And there's also a periodical that has more detailed information on the content that's included in this presentation that you can access as well. So RIEGL has a number of bathymetric sensors that operate in the near and onshore environments. These include the VQ840G, which is a relatively compact sensor. It's deployed on heavy lift drones, helicopters, and even small aircraft. Typical flight altitudes generally range from about 75 to 200 meters AGL. The dual wavelength VQ880G2 is a little larger. It's similar in form factor to our traditional airborne topo-only sensors. It includes an internal camera option. You can put 150 4-band cameras in there, 150 megapixel 4-band cameras. It also has a form factor that supports gyro stabilization and demonstrates approximately about a 3 times increase in collection efficiency over the smaller VQ840G. And this is due to its higher output laser and resultant higher flight altitudes. Both sensors are capable of close to 2.5 Secchi depth penetration capability, depending on processing methods, water turbidity, and bottom substrate reflectivity. And both sensors are also filling a niche where maximum depth penetration is not necessarily the primary design element, but rather offers sensor alternatives where smaller size, lower cost, and higher resolutions might be required. And here's an example of the 880G. It's installed, in this case, in a Cessna 206. So it's about the size of a large format camera and takes up relatively little room in the cabin. And typical installations are into a standard 19-inch camera hole. In terms of the 840G, because of its size, we can consider a multitude of different platforms. In this case, this is a newly released VQX wing pod that has been configured for the 840G. And the form factor also supports gyro stabilization if that's of interest as well. This is the same sensor now installed on a helicopter. In this case, GEO1 has installed it on a nose mount, on a Meeker nose mount. And in this installation example, it also includes a phase 1 150 megapixel camera. And of course, the sensor can also be installed on a heavy lift drone. This is a configuration that's becoming more popular. It is a little bit larger than the smaller lightweight drones that would not be able to handle this payload. This payload comes in around 12 to 13 kilograms. But for larger areas, inland ways where you have licensing to support a heavy lift drone application, this configuration is becoming more popular. So there's a number of environmental variables impact water penetration and bottom detection success. And of course, these include water turbidity, bottom reflectance, surface roughness, angle of incidence, those sorts of things. And users generally have little control over these parameters, but they do have control over various sensor parameters. but not only sensor parameters, but also various processing methods. And RIEGL offers several approaches, including online and full waveform processing, but also various sub-methods of waveform processing. In this example, we can see the relatively low noise associated with online full waveform processing in blue. And the noisier full waveform processing is a result of algorithms that have been specifically developed to extract much more information from the range files. And these are optimized for bottom detection, much more so than the online range extraction methods only. The bottom surface height discrepancy you see in the graphic is due to the refraction correction for water that has been applied to the full waveform processing methods already. The VQ840G emits short laser pulses at a wavelength of about 532 nanometers, so in the green. The laser pulses interact with the target, and a small fraction of the signal reflected into the direction of the instrument is collected by the receiver lens, and then it's converted into an electrical signal. This signal is amplified, filtered, and digitized, and a detection unit usually triggers the analysis of samples potentially corresponding to a target by online waveform processing or by the full waveform processing. Besides the fact that range and amplitude information is calculated in real time and stored directly, online waveform processing by means of system response fitting offers advantages concerning measurement accuracy and precision over large dynamic amplitude range of the echo signals. But it does, however, have its limitations when it comes to situations with overlapping echo pulses. Both the accuracy and the spatial resolution can suffer from the fact that online full waveform processing analyzes the echo signal peak by peak instead of considering the entire waveform, as in the case with for example, Gaussian decomposition of the full waveform. So in this example, we evaluated depth performance differences using two different processing methods, the online waveform processing I just mentioned, and a full waveform processing approach. This area was flown with the VQ840G on a UAV platform from about 50 to 60 meters. Maximum water depths for this area amounted to approximately 2.4 meters. And you can tell from the images, the water quality was visibly turbid, but the bottom substrate was relatively low in organic content and reflected well. In this slide, the left contour plot shows what was possible using online waveform processing only. But you can see that it's missing some contours in this section in orange. And conversely, if you look at the full waveform processing method on the right, the algorithm was able to extract more depth information. So the right graphic shows the added depth performance possible when using a full waveform approach. In fact, in this case, an additional ½ meter was possible, enabling complete detection of the river bottom in this example. In this example, we compare full waveform processing methods for extending bottom detection success by considering full waveform averaging or waveform stacking methods. The project site was located in the south of France in the Mediterranean, again using the 840G. The sensor was flown on a small Cessna 206, like an example I showed earlier, at approximately 150 meters AGL and 110 knots. This slide shows the sensor parameters that were derived for this mission. The beam divergence was quite small, 0.003 milliradians. You can see this down here in the lower left. So it's to maximize target resolutions, and the parameters also provided a point density of about 8 points per square meter when flown at 110 knots. You can observe the relatively uniform point pattern that was created with the sensor parameters optimized for the platform speed and altitude. And the high redundancy at the ends that you can see in this graphic in the lower right is of course related to the conical scan geometry. These points can of course be removed during post-processing if desired. The survey was flown in a block configuration parallel to the shore, and there's a cross strip. As you can see, it's flown perpendicular to those parallel lines to control the survey accuracies, but also evaluate bottom surface detection limits. And this is a profile view of the LiDAR model showing the above and below water features surrounding Les Deux Frères Islands in the Mediterranean. Now, when we look at the depth results associated with the sensor, the data was first processed using full waveform processing. And it was computed using exponential decomposition methods and realized a maximum depth of about 17.5 meters. Secondly, waveform averaging was then applied to the results to improve the signal to noise ratio and include bottom returns that were previously excluded from the data set. And this yielded an additional 4 meters of bottom surface detection capability for this data set. Now, there are pros and there are cons. And yes, of course, we got extended depth performance, but through averaging, as you can imagine, you are simplifying the topology to some extent. So in this area where the topology is relatively uniform, there's not a lot of complexity, then the averaging approach works extremely well. But there is, of course, resolution loss. And so this approach may be less successful in narrow, complex waterways, but that may be partly mitigated by higher density data sets in those smaller, more complex waterways. So this is an area that we're expanding on and doing more analysis, and we'll be announcing this capability to our Bathy sensor owners very shortly with the software release. Now, a closer look at the VQ840G sensor specification shows a relatively compact, fully integrated sensor. What's significantly different, though, is that RIEGL has allowed users more control over some of the sensor parameters to optimize the sensor for various operational and environmental conditions. And the next few slides will analyze the effects laser beam divergence in the receiver field of view have on detection success. Linear mode LiDAR systems typically employ a laser beam collimator to focus the output energy to the ground. And this results in an expansion of the beam footprint as it propagates through the atmosphere. However, this beam expansion is more dramatic when it propagates also through the water column and back to the receiver. Therefore, including the ability to modify the receiver field of view detection window size may be a useful parameter for maximizing detection success. The interplay between laser beam divergence and receiver field of view in airborne bathymetric LiDAR has a strong influence on spatial resolution and depth performance when measuring into the water, and also vegetation penetration. Spatial resolution is ultimately limited by the laser footprint size on the ground, so a low beam divergence is usually preferable. Under circumstances, the capability of measuring through vegetation to the ground may be improved by using a larger beam divergence. The receiver field of view is usually kept as small as possible in order not to collect an unnecessary amount of background radiation. For bathymetric laser scanning, a large field of view enables the receiver to pick up more of the laser signal scattered on its way through the water column. In this analysis, we systematically investigated the effects of varying both parameters of the RIEGL 840G airborne topo-bathy sensor. And the chart shows the sensor parameter matrix that was developed for the collection effort. The project site for this analysis included both small water bodies located near the Pilac River in Austria, as well as some forested areas. Average flight altitude was approximately 200 meters AGL, producing a ground swath width of approximately 150 meters with the 40-degree field of view. For the water surface returns, one would expect no dependence of the amplitude on the laser beam divergence in the receiver field of view, as long as the divergence is comfortably larger than the receiver field of view, or as long as the receiver sees the entire laser footprint on the surface and provides some margin allowing for lag angle effects. When we plot out the colors in this chart based on the amplitude of the in decibels over the detection limit, what we see is that the for 1 milliradian laser beam divergence and 3 milliradian receiver field of view, it falls short of the expectation. So in this area right here, these blue returns. And this returns get quite sparse for this setting. So generally speaking, the smallest receiver field of view significantly limits sensor performance. For bottom returns, we see a strong dependence of the performance on the receiver field of view, but none on the laser beam divergence. The amplitude decreases by more than 2 decibels when going from 18 millirads to 12 receiver field of view, and by another 3 decibels for 9 milliradians. At a receiver field of view of 3 millirads, we're obviously at the performance limit of the instrument as the returns from the bottom are becoming sparse. And this causes the number of points available for analysis to be very small. And therefore, the amplitude values presented are not reliable. We would not recommend using such a low field of view for reliable bottom detection. Another aspect of our analysis is the dependence of the number of multiple target echoes on laser beam divergence in vegetation measurements. So the proposition of this study is that using a larger laser beam divergence corresponds to a larger laser footprint on the target and would result in a correspondingly higher number of multiple target echoes or more returns. To test this, we analyzed data of 4 scans acquired at laser beam divergences of 1, 3, 4, and 6 milliradians over partly forested areas, and in this case was under leaf-off conditions. We would expect no dependence of the receiver field of view on the number of target returns. Therefore, only the data sets with a receiver field of view of 9 milliradians and 12 are used in this example. And in order to maintain an identical geometry for all scans, the same area was scanned from an altitude of 200 meters above ground as per the project site that I showed earlier. Now, in this case, if we look at the graphs associated with this, basically the number of multiple echo returns shows that a large beam divergence results in a larger number of multiple echo. And this is plausible considering the object structure sizes in relation to the laser footprint. A large beam spot is more likely to strike multiple objects such as foliage or branches at different heights of the vegetation. And with decreasing beam divergence, the size of the laser footprint approaches the object size and the number of single return echoes increases, while the number of multiple echoes decreases. And another aspect worth analyzing is the distribution of the range differences of multiple target returns, or the histogram of the distances between first and last echo. So that separation distance. And the histogram shows a fairly similar distribution of distances for beam divergences of 3, 4, and 6 milliradians. However, for scan data acquired at 1 milliradian, there's a higher number of short target distances below 3 meters. And while distance differences between 3 and 16 meters appear less frequent. The pronounced peak at ranges of around 4 meters, which does not occur in the scan data acquired at a beam divergence of 1 milliradian, it could be attributed to the correlation between the size of the gaps in the forest canopy and the laser footprints. But while it may be attractive to increase the laser beam divergence in order to increase the number of return echoes, this will at the same time result in a reduced spatial accuracy and resolution due to the larger laser footprint. However, to be able to receive echoes from weakly reflecting targets, it would in this case also be necessary to maintain the same laser power density on the ground targets, which is only possible with a stronger laser source. And this would imply a higher power consumption, size, weight, and price of the LiDAR instrument, of course. In that sense, it's apparent that high pulse repetition rate and small beam divergence pays off by achieving multiple target capability, good vegetation penetration, and high measurement accuracy at the same time. So when we look at the pros and cons of all these different approaches, on the processing side, if we look at only say the online waveform processing method, yes, it's got much lower noise, as you saw in that earlier slide. The water surface bias is definitely lower, and it does result in smaller data volumes, as you would imagine, without capturing the full waveform. But the detection is poor, and you have no confidence values associated with that detection success. With the full waveform, of course, we get much more metadata information, more attributes. It allows us to consider things like pre-classification. We have improved detection. We have algorithms that are basically optimized for detecting those low or weaker signals. But the disadvantage is you are bringing in more noise, requires some filtering. Of course, full waveform has larger data volumes and inherently, therefore, longer processing efforts. Looking at full waveform averaging as it relates to full waveform processing, we talked about extended depth performance, but there is a generalization of the data that occurs as you would expect through averaging. And while I have here, it says it can't be used with complex topology. I would say that the success is you generalize that complex topology more greatly. I would suggest using a higher density collection for those types of environments. The receiver field of view, I think, is a great way to be able to allow users to optimize the sensor for different environmental and collection scenarios so we can improve detection. But there is sensitivity to saturation, right? If you open up that receiver field of view all the way, you are bringing in background radiation, and it can significantly impact the range measurement performance. And when it comes to the use of the beam divergence, the smaller the beam divergence, the better your resolution is, of course. But there are constraints when it comes to eye safety considerations, and so you have to keep that in mind, the minimum permissible exposures as it relates to the beam divergence and the required altitudes. And so in conclusion, in terms of processing operational guidelines, the online waveform processing is excellent for high resolution surveys where bottom detection is guaranteed. The full waveform really is the industry standard for maximizing water depth penetration success, and being able to leverage those additional attributes for things like collection confidence or detection confidence values as well. And it's full waveform, actually this should say averaging, full waveform averaging, excellent tool to extend depth performance. And as we mentioned for laser beam divergence, really choose as small as value as you can that allows eye safe operation for the flight altitudes that you're constrained to. It provides better resolution in the long run at higher point densities. And with respect to the receiver field of view, we would suggest at least a 3 times size over the beam divergence value. Larger if possible, but of course you do have the implications of oversaturation that might occur under certain collection conditions. So that's our presentation. I do have time for some questions. If anyone has some, I will stick around. One question, not sure why I have no audio. I sure hope everyone heard this. And I don't have an update on that. But as of now, I have no further questions. So if you would like, please send us an email. We can provide further information. The PowerPoint presentation will be made available in the near future on our website portal. And please download the handouts. As I mentioned, there is an article that provides more detail specifically on the beam parameters and their impact on topo-bathymetric LiDAR sensor performance. Have a great day, everyone.